Oh,
Okay. Thank you for the invitation. This, whenever I get to new stuff, will all be joint work with Hoai Dao, a graduate student at Oklahoma State. I want to set up the standard background for talks about resolutions. S is going to be a polynomial ring and variables. I will be a monomial ideal. In all the examples, we use variables ABC or ABCD rather than having to chase subscripts around. So first, a reminder of the main object of interest. Free resolution is an exact sequence of free modules that ends in I. So F0 will surject onto I, and F1 will surject onto the kernel of the previous map, and so on all the way back. By Hilbert's syzygy theorem, in this setting, that will always terminate at some projective dimension, and so you get to stop. Because we have a monomial ideal, it's multigraded, and that means that these free resolutions are also all multigraded. So in particular, every one of the free modules we can write as a direct sum of twisted modules twisted in a multi-degree M. The multi-degrees are naturally in bijection with the monomials. So S parentheses M inverse just means the generator has multi-degree M raised to some power. And then all of the differential maps are going to preserve multi-degree. This is not the way the books handle it, but I think it's the right motivation. The resolution is minimal precisely if all those exponents are as small as possible. That means that each of the summands has minimal possible rank over all free resolutions of the ideal I. It is a moderately difficult theorem that minimal resolutions exist. It's certainly not obvious when we define it this way. And what's more, we can recognize minimal resolutions if we look at the matrices of the differential maps. You're minimal precisely when there are no non-zero scalars in those matrices. And what's more, in addition to existing, they're unique up to isomorphism, which for my purposes means up to choice of basis. And so one of the underlying goals in the study of resolutions of monomial ideals is to be able to understand how the minimal resolution looks, possibly by choosing and understanding a convenient basis. So I want to start with a fairly standard example. I apologize to experts that I'm just building the Koszul complex here. There's going to be a little bit of notation that's introduced as well. So how do we resolve a fairly straightforward ideal like the one generated by A, B, and C? Well, you have three minimal generators for the ideal. So if we want a free module to surject onto that, we're going to need a basis element to hit each of the minimal generators. So we need three of them. And we're going to have that basis be given by these formal symbols, bracket A, bracket B, bracket C. Each of them we assign homological degree 0, and we assign it a multi-degree that's the same as its name. So the differential map will send each of them to just remove the bracket. And so we get to begin our resolution. We have a direct sum of three rank 1 free modules, all just times the appropriate formal symbol. Bracket A goes to A, and so on. So shove that up into the corner. What comes next, I need to figure out what's in the kernel of this map. So what linear combinations of bracket A, bracket B, and bracket C are mapped to 0. And there are three tautological, I guess elementary, what do we call them? These basic things which are called syzygies that do get sent to zero. If you take b times bracket a and apply the differential, you get ab. If you take a times bracket b and apply the differential, you also get ab. So if you subtract them, that goes to zero. Therefore, we have these three elements of the kernel. So the next stage of the resolution, I need to have something that hits each of those elements in my first free module. So I'm going to again define formal symbols. We'll call them by pairs AB or AC or BC. They're going to have now homological degree 1, and their multi-degrees are forced. B times bracket A has multi-degree B times the multi-degree of bracket A, which is to say AB. So that symbol AB must also have multi-degree AB, and similarly for the others. And so we assign the differential now to send each of these symbols to that syzygy, and we get this as the next stage of our map. So we again have a rank 3 free module. The symbol AB gets mapped to B times A, negative B times A, plus A times B, and so on. And if we stare at this a little bit and wonder if there's a kernel, we might notice that if you take, what do I need? C times the first column and B times the second column and A times the third column and add them all up with a minus sign somewhere, everything would go away. So there is one more thing. C times AB minus B times AC plus A times BC gets mapped to zero here. And if you stare a little more, you'll eventually convince yourself that that's it. So the next module over, we're going to need to hit that syzygy. So we create a new formal symbol, which we're going to call ABC. It's got homological degree 2, it's got multi-degree ABC, and it gets mapped to that expression. And so when the dust clears, we have this resolution for the maximal ideal in 3 variables, ABC. This is a very famous thing. It's called the Koszul complex. It works out great because those form a regular sequence. But it's also an example of something called the Taylor resolution. So the legend goes that long before I was born, Kaplansky told Diana Taylor, his graduate student, to just figure out how all the monomial resolutions look. This shouldn't be too hard. And this is a problem that's, as it turns out, is very hard. It's been wide open ever since. There's been substantial progress in the last 5 or 6 years, with people being able to finally write down explicit resolutions that don't involve making choices anywhere along the way. But it's a really hard problem to understand, and Taylor was able to at least not get a minimal resolution, but a resolution which has a lot of nice symmetry properties for an arbitrary monomial ideal. In particular, suppose you have S generators, then you look at all the subsets of the generating set. And for every subset sigma, you're just going to make a formal symbol for sigma. Its homological degree is going to be sigma or subtract 1 because you always subtract 1. And its multi-degree will be the least common multiple of the generators inside it. And the map is that you send it to, for every generator inside sigma, you can remove that to get a new subset tau. And you want to map it to a multiple of the formal symbol for tau. But the degree of sigma is probably larger than the degree of tau, so you have to multiply by an appropriate correction factor. And then finally, there's a plus or minus because when you're doing homology things, there's always some alternating sign going on. And I could not be bothered to try to write out the necessary extra subscripts and superscripts to specify the plus or the minus. Hopefully people are okay with that. So that's sort of a universal resolution, which is not minimal for an arbitrary ideal. But I want to pause and take a digression into basic algebraic topology because they are closely related, and the topology gives us some good, useful intuition for what's going on. So if you have a simplicial complex gamma on some variables v1 to vs, then you're going to build a chain complex in order to compute the homology of the underlying topological objects. The chains in the ith position are just the free module with basis consisting of all the faces of gamma that have dimension I. And the differential is you map a face to, for every vertex, you remove it, and then you assign a plus or minus in the standard way. And when we do that for example, the two simplex, you'll notice that it's almost exactly the same thing as we got when we built the Taylor resolution of this ideal with three generators. The only difference is that on the bottom, we have a bunch of multi-degrees. So the generators for each of the free modules have multi-degree A or B or C or AB or whatever. And that means that the differential maps, in order to keep the degrees from changing, you need to multiply by some monomial, which is always the quotient, the degree of the target row, the degree of the source column divided by the degree of the target row. But otherwise, these things are exactly the same. So in particular, if we had started with a two simplex and decided that its vertices were named for the generators, we could take that chain complex, force multi-degrees onto it, and we'd get this Taylor resolution. So the basic idea here is that many resolutions of monomial ideals can be built out of combinatorial topology this way. So let I be any monomial ideal on S generators, and gamma a simplicial complex on S vertices whose names are the same as the names of the generators. Then for every face of gamma, we're going to define a formal symbol corresponding to that face. It'll have homological degree the same as the dimension of the face, and multi-degree given by that least common multiple of its vertices. And in the chain complex for commuting the homology of delta of gamma, there's a differential map. Sigma gets sent to some sort of sum over all the other faces of 0, 1, or -1 times that face. So I'm just going to call that 0, 1, or -1 epsilon sub sigma tau. And we're going to build the differential for hopefully our free resolution by just taking that same thing and inserting what's necessary to make the multi-degrees work out, which is always just this additional fraction degree of sigma divided by degree of tau. And if we're lucky, if we've been living right, the resulting complex of free modules will be exact. And when that happens, we get a resolution of I. We call it a simplicial resolution that's supported on this particular simplicial complex. So a couple of examples, but also what this does is it allows us to have some intuition. We can think about our resolutions not as some horrible sequence of giant direct sums of modules and matrices that are hard to read, but just as some sort of simplicial complex. So the Taylor resolution, it turns out, it's always a simplicial resolution, always supported on the full simplex of its generators, but it's not necessarily minimal. So, for example, this picture here shows the Taylor resolution on the left for the ideal a squared, ab, and b cubed. And notice that the big face consisting of all three generators has the same multi-degree as the edge on the bottom, because the LCM of a squared and b cubed is equal to the LCM of all three things. And so that means that somehow the bottom edge is redundant and the big syzygy of degree 2 is just measuring its redundancy. So we should be able to delete that edge and the corresponding big face. And this lambda-shaped simplicial complex over on the right is also a resolution for this ideal. And in this case, it happens to be minimal. When there are simplicial resolutions, and in particular, when there are minimal simplicial resolutions, sometimes there's choice. So for example, if you take all the square-free monomials of degree 2 in three variables, a, b, ac, and bc, the LCM of all three of them is equal to the LCM of any two. So again, if we built the Taylor resolution, the interior triangular face would have multi-degree ABC, as do all three of the sides. So we can delete the interior face and any one of the sides simultaneously, and that ideal has three simplicial complexes that represent its resolution. Okay. So the big result about these simplicial complex ideas is that to check exactness, you don't have to work all the way through your complex and painstakingly compute kernels and images. Instead, there is a combinatorial check for whether or not you've found a resolution. So suppose that you have an ideal I, and you've got a simplicial complex gamma on its generators, which you're hoping supports a resolution. It turns out that it does precisely if for every multi-degree M, the induced subcomplex where you throw out all the faces whose multi-degrees don't divide M, if that's always acyclic, then you've got a resolution. And if it's ever not acyclic, you don't. So for example, this thing here where my gamma is just three dots and I'm trying to resolve a squared, ab, and b cubed, that is not going to support resolution of I, because for example, if I look at m equal to a squared b, then the induced subcomplex, I'll get to throw out the b squared, but I'm still left with two dots, a squared and ab, that are not connected. And if we're not connected, then our, what is that, zeroth homology is non-trivial. So we are not acyclic. The proof of this theorem is, well, look at the complex you build F that you're hoping is a resolution. And because F is a multi-graded complex, it's exact if and only if when you slice it at every multi-degree M and look at the resulting complex of vector spaces, those all need to be exact. But if we look at what that slice is, it's a complex of vector spaces. What's the basis everywhere? Well, the vector space is non-trivial if and only if the ring S times sigma contains something in multi-degree M. And that'll only happen precisely when M is a multi-degree of, when M is a multiple of the multi-degree of sigma, because then you can take the formal symbol sigma, multiply it by the quotient, and get somebody in your module that does have multi-degree M. So this happens precisely when sigma is in gamma less than m, the thing that we're saying has to be acyclic. So if these are all exact, we're in good shape, and they're all exact precisely when this thing on the right, which is remove the multi-degree, and you're looking at the usual chain complex that you use to compute the homology of gamma less than m. So there is a topological way to check whether or not your simplicial complex turns out to support a resolution. So the bad news and the good news. The bad news is that most of the time, unless your monomials are in some sense very sparse, you are not going to have a simplicial resolution that is close to the minimal resolution of your ideal. The good news is, if we go back and look at the way we constructed a simplicial resolution, nothing here actually cared that we had a simplicial complex. It just cared that we had some sort of combinatorial objects that had differential functions that only took you down by 1 degree. So in particular, if you take a polytopal complex and just copy that definition, or even a regular cellular complex and just copy that definition over, you'll be able to talk about a polytopal complex that supports a resolution, which we could call a polytopal resolution, or a cellular complex, so we can talk about cellular resolutions of an ideal. And when we do this, there's a lot of room to actually find minimal resolutions in many cases, and there's a lot of room to explore. For example, this square down here, it's not a simplicial complex because it's only got one two-dimensional face, but it does support the minimal resolution of the ideal generated by those 4 variables, A, B, B, C, C, D, and AD. The bad news is that you can find monomial ideals that are so bad that their minimal resolutions can't be supported on any kind of reasonable topological object, including a CW complex. And I tend to think that this result is a really big deal. It means that the category of monomial ideals is a lot more complicated than one might guess. Anyway, what I'm interested in is studying ideals whose generating sets are dense in the sense of like the Newton polytope. So what I want you to think about is take the exponent vectors of your monomial generators and think about them as vectors. They can live in R to the n. In the picture, that's R3. And so every lattice point in the first orthant corresponds to a monomial. If we take that first orthant and slice it with a hyperplane that just measures the degree, the sum of the entries being 3 in this case, then we get what I guess you would call a dilated simplex with a bunch of lattice points inside it that represents all monomials of a given degree. In particular, when you have 3 variables, you get a nice triangle with a bunch of dots inside. And so I'm interested in studying the resolutions of ideals that in some sense contain almost all of these lattice points among their generators. The best known resolution in this situation is the Eliyahu-Crever resolution. It resolves a large class of ideals, which includes powers of the maximal ideal. And I'm not going to talk about it in any depth except to point out that it's here. It is a cellular resolution. In three variables, the cells are the diamonds and the triangles that you see on the left. And the various line segments are the degree one stuff, and the vertices are the generators. And that's nice and polytopal and a very simple picture. In four variables, I tried to produce a picture of the cube or the fourth power of the maximal ideal, and it just got way too busy, and I couldn't even tell what I was looking at anymore. It's a little bit messier. We still have in the bottom corners those two three simplices, but then there are two more cells, something with the d squared in it that's almost a cube, but a cube doesn't fit there, and something weirder on the top that has the c squared in it. It is a regular complex, but it's not polytopal. In particular, that bottom thing that looks almost like a cube, it's got boundary that consists of the two bluish simplices here with vertices A, B, C, D, and either AC or BC. So it contains the points AC and BC, but none of the line segment between them. And Eliahu-Curvaire is very nice. It's got excellent combinatorial properties that help us count things like Benny numbers, but unfortunately, it's not polytopal. There is a standard construction called the complex of boxes that remedies this. It's always polytopal. And it again resolves a large class of ideals, including powers of the maximal ideal. So I've got the corresponding pictures for the same two ideals. For the in three variables, somehow you've got the same thing. You've got a bunch of rhombuses and triangles along one edge, but somehow which edge the orientation of the rhombuses has changed. This has always bothered me. There's sort of a lack of symmetry between the two resolutions, which makes me uncomfortable. In four variables, you chop the simplex up, and what you are seeing is along the edge from A squared to D squared, there are three simplices, and then there are also two triangular prisms. Again, if I could have drawn a higher power, we'd see more cubes to justify the name complex of boxes. So I would like to take a minute to introduce the complex of boxes, because I know that I struggled way too long to understand how it works. And it's going to be the main tool if I manage to get to new stuff. So for any set of variables A, we're going to build an elementary box, which I'll call delta A. That's just a simplex that has the elements of A as its vertices. And then a box will be a product of these things. So this figure is stolen from our paper. So on the left, we have a box which is the product of the box on A, B, and C, that's in red on the left, and the box on C and D, that's in blue on the left. And so their product is a triangular prism. On the right, we have a box that's a product of three lines, AB times BC times CD. And it's objects like this that I think are where the name comes from, that they really do. When you product a bunch of pairs, you get something that looks like a familiar box. And so the construction of the complex of boxes is that for every generator of your ideal, you're going to build a box gamma M as a product of elementary boxes that are associated somehow to those variables. And we haven't found a really good way to write clearly what the association is. So I'm going to go by example. The first box always starts with A and ends with whatever the first variable is dividing your monomial. The next box starts with the first variable dividing your monomial and ends with the second variable. The next box goes from the second variable to the third variable and so on. So for example, when we're looking at AB squared D, the second and third variables are the same. So the third box is just a point B. When we look at something like that guy on the bottom, ACDH, well, there's an awful lot of variables in between D and H. So there's a 5-vertex simplex showing up in the product. And then if you have an ideal I, the complex of boxes is a polytopal complex that you just get by grabbing one of these gammas for each generator. So here it is for the cube of the maximal ideal in 3 variables. That thing on the bottom left is gamma of B cubed. Is gamma of, the thing on the bottom right is gamma of B squared C, which is the box AB, horizontal line, times B times the box BC, a line that's slanting up and to the left. The thing on the very top, the triangle, is gamma of C cubes. So you've got the box ABC times C times C. And you can do likewise for all of these things to figure out which box they are. So the observation I want to make is that both the complex of boxes and the Eliyahu-Curvaire resolution, all the cells in the polytopal complex that we build really want to be cubes. And the reason they're not seems to be that they run into the boundary of the simplex before they run out of room. So if we could kind of allow ourselves to make some of the variables have negative exponents, we could expand the boxes we see into hypercubes of whatever the appropriate dimension is, as has been done here. And for that matter, if we take the complex of boxes for the square of the maximal ideal in 4 variables, in black on the right are the cells that show up, and I've colored in orange the elementary vectors that correspond to a particular action, what's called a elementary Borel move, on the generator, and in green the rest of the box. And so what you can hopefully kind of see is that the box that we're seeing is built up of some edges, but also some diagonals of the box that really wants to be there. But the extra stuff is going into territory where some of the variables have a negative exponent, and that's not allowed. So somehow whatever's going on is that in order to build a resolution of the power of the maximal ideal, you really want to take the lattice point construction and chop it into cubes. And I'm going to mess with that idea. Okay, so one more bit of background that I'm not going to talk about a lot. But we need the vocabulary. An ideal is called Borel if it satisfies the exchange property that you can switch any monomial that's divisible by an xj, change the xj to an earlier variable xi, and you can do that without leaving the ideal. These things are super important in a lot of ways. They show up as generic initial ideals, so they bound a lot of invariance for arbitrary ideals. They are resolved, all of them, by the Eliyahu-Curvaire resolution, whatever that is. So they let us do a lot of counting of things like their Betty numbers and their Hilbert function in straightforward ways. So they bound things and we can figure out what bounds they're using. They're super nice. A particularly nice example of Borel ideals are principal Borel ideals. That's just where you take some generator M and you find the smallest Borel ideal that contains it. So for example, the principal Borel ideal generated by A, B, and C, we have to keep that A and A, but the B could change to an A and the C could change to an A or a B. And when you look at everything that arises when you make those moves, you get these 5 monomials. So Borel ideals also have the property that the complex of boxes minimally resolves them. And so I want to use them to build a new resolution that has the cyclic symmetry I was complaining a minute ago wasn't there in the complex of boxes. So fix any monomial M and take the principal Borel ideal generated by M. But then switch up the order. Move x1 from the first variable all the way back to the last variable. And take the principal Borel ideal generated by M, but with respect to this new ordering of variables. And then switch up the order again. Now move x2 all the way to the back, take the principal Borel ideal generated by M with respect to these, and keep going. It turns out that the power of the maximal ideal is the sum of all of these principal Borel ideals for the same monomial M. And the sum is particularly nice. They don't overlap in any significant way. So here our M is ABC squared. The stuff in yellow on the bottom left is the principal Borel ideal generated by M. The stuff on the right in green is where we have switched the order. So B comes first, followed by C, then A. And the stuff on the top in blue is where C comes first. But all 3 of those colorings are principal Borel ideals. And if we take the complex of boxes for those ideals, they look exactly like we see in this picture, where the yellow stuff is subdivided into rhombuses of one orientation. The green stuff, the rhombuses have a different orientation, and the blue stuff, they have yet a third orientation. And this now has the property that it is reasonably close to symmetric. In particular, there are triangles in every corner. And if we try to spin it around the center, ABC squared, it really does have cyclic symmetry. So this gives us what seems to be an entirely new minimal resolution or basis for the minimal resolution of, in this case, the 5th power of the maximal ideal in 3 variables. And this is a game we can play with any power of any maximal ideal. And I think it produces a nice resolution that has a bunch of interesting properties. Okay, so the question that I had is, what happens if you take a power of the maximal ideal and remove all the remove one generator from it? And I tried to call this a pinch Veronese ideal, and people who do toric varieties told me that no, I can't do that. So we're calling it a pinch power. And this is something that I think people are reasonably familiar with the Betti numbers, but if there was knowledge of how to resolve the thing in general, it was at best hidden inside much more general results. So ask around, I think most people don't know what the resolution looks like, although people do know at least the combinatorics of it. So can we resolve this? And this is new work, mostly due to Hoai Dao. And the plan is, from the polytopal perspective, this is pretty straightforward. Take the boxes that meet at that monomial here. So the yellow, green, and blue box meeting in the center there, forming a hexagon, and treat them as a topological space and just merge them, and you'll get, in the 3-variable case, a hexagon with that deleted variable in the center. And that hexagon becomes part of a polytopal complex. And the main result is that this is now a minimal resolution of this ideal. So we have a nice way to minimally resolve these pinch powers. That's a polytopal resolution that has a lot of nice symmetry around the removed power. And yeah, that was our goal. In 4 variables, the picture is much messier. When we glue together 4 boxes around a deleted thing, in this case, it's just the product of all 4 variables, A, B, C, D in the middle. We come up with that shape in the middle, which I think is called a rhombic dodecahedron. And then that's glued together with a bunch of other more familiar boxes. And this picture was generated by Hoai, which is the best we've been able to do to really visualize what's going on, to pull all the other things apart from it, and just imagine shoving everything together. So I talked a little faster than I planned to, but maybe this is a chance to pause. I have a little bit more stuff prepared, but not 40 minutes more stuff. Can I call for questions or anything? And am I correct that I have about 10 or 15 minutes to work with?
Jeff, would you return for a moment to the
Yes.
construction for the maximal ideal, the symmetric construction? I didn't take enough of the details to reproduce it.
Okay, so this picture.
Yeah. So how did you choose those boxes?
So the yellow ones are just the complex of boxes. So that's a completely standard construction, which looks like this. The green ones on the right, we've done the same thing, except we have reordered the variables as in I2 here,
right,
so that BX2 is the cheapest variable and AX1 is the most expensive variable. And upon doing that, we are still taking the complex of boxes for the Borel ideal generated by ABC squared. It's just, I guess I should call it BC squared A now.
How did you choose ABC squared as the?
That was completely arbitrary. We can do this for any monomial you'd like, or yeah, any monomial you'd like in the power.
Okay, good. Now I understand, I think.
Yeah. Okay, cool.
Good. Pretty picture.
Yeah, I really like the pictures. Okay. Anybody else?
Yes,
I'm gonna
ask, can you leave out two?
Yes, please. Sorry?
Can you leave out 2 monomials?
Yes. So I had thought that I had a working web camera and I was going to do some sketching on the board. So you can leave out 2 or more monomials. We do not have a as thorough a picture as we had hoped we would get for free from this. So let's say that we want to leave out the two monomials at the center of those two gray hexagons on top. So the natural thing is to just plunk down those two gray hexagons and then copy the red and blue and yellow things into the rest of the picture. But unfortunately, what happens when we do that is there's typically going to be some region that if we remove the two things separately, we have a disagreement on what orientation to use the remaining boxes. And so far, almost all the time, we've been able to ad hoc find ways, every example we can come up with, to fill that region in. As I suspect, you can all look at this picture and fill in some lines to get those rhombuses and two more squares to work in the bottom picture where we've deleted two generators. There are some restrictions that are necessary. If we tile, even working in three variables, if we tile the big, I guess you'd call it a dilated simplex with black triangles that are oriented upwards and white triangles that are oriented downwards like a checkerboard, then you're going to get an excess of black triangles, one extra per degree that you're looking at. And you've got every box that you attempt to put in is either going to cover one black and one white triangle, or it's going to be a triangle that covers a black triangle. So if we remove a bunch of these hexagons, we have to make sure that we don't create a situation like, does this annotate button work? No, it does not. Like if we are trying to also remove a b cubed c from this, so we'll get another hexagon, three hexagons that are mutually similar around the center there, and we'll have an upside down oriented triangle in the middle. That can't be covered by a box, so this technique will not resolve it. And there's got to be some analog of that in higher dimensions as well.
Jeff, do you want to try annotating? Oh, sorry, didn't mean to interrupt you, but if you want to annotate, why don't you, I'm going to try to make you a co-host and see if that lets you annotate.
Oh, maybe that'll work.
I just made you a co-host, so why don't you try?
Okay, so if I click on this button, it gives me a color, so I can grab black. And so, yeah, if we were to try to remove a b cubed c here, and just make that, whoops.
We got the idea, though.
Yeah, and make that a hexagon. That thing in the middle is a problem. Now, it is the case that there is a perfectly good regular cellular resolution of this thing where you just grab that thing in the middle and attach it to any one of the three hexagons. But somehow that feels like cheating because we're not using boxes in the same way. So in general, oh, that's interesting. Let me say something about what is the gray hexagon, right? So I did this. Okay. So in three variables, we saw a hexagon. In four variables, it's this thing, which, if I read the table of Aristotelian solids correctly, is called rhombic dodecahedron. In more variables, it is complicated. I've not encountered lists of Aristotelian hypersolids, so I don't know if there are names, but when I typed the F vectors into OEIS, nothing came up. So whatever the shape is in more variables seems to be a relatively new thing. You build it by you're meeting a bunch of cubes, which you can realize as just taking unit hypercubes on all the hyperplanes, the coordinate hyperplanes at the origin, and then taking the whole thing and projecting it out onto the hyperplane, the sum of the variables equals 1. But I don't know a name for that. Dave Beyer has a lecture notes on his website where he talks about corners. And that's the closest thing to any discussion of this I'd ever seen before. So he would call it a corner whose probe cube consists of a single vertex. Until 2 weeks ago on 3 Blue, 1 Brown, Grant Sanderson talked about what he was just thinking of as geometry puzzles, but which have exactly this idea of corners showing up. And so you can sort of imagine these places where the 3 rhombuses are meeting as exterior vertices in a staircase diagram, like on the right. And so the best answer I can give right now is entirely conjectural, because even my 3-dimensional intuition is a disaster, and I'm not quite sure how to phrase the projections when we have boxes that are really trying to get outside of our simplex. But my conjecture is going to be that there is always a translation from the triangle we're looking at, which is a projection of the first orthants. We should be able to translate staircase diagrams like that thing on the right there into the sort of outermost vertices of the staircases correspond to where we're able to bring our things together. Those are going to be the central points that we want to delete. So it's probably the case that if you want to delete 2 variables, you need to be able to build a staircase diagram like this, such that each monomial is at the outermost corner of one of those blocks. But that's a guess right now. And then one other thing that I think is a natural question: do we have to remove the monomial from the interior? And the answer is no, you totally don't, because if you want to remove it from the outside, you can still build, whoops. Okay, I can't actually annotate correctly, but you can still build out that thing. It's just that half of it is going to be missing because it heads off into not part of the simplex land. And this is totally fine. The only issue is if you try to remove an actual corner like a pure power, then you're looking at just a Borel with holes ideal, which was studied by Aramova, Hebe, and Herzog, or Aramova, Avramov, and Herzog, or Charalombus and Evans, one of those groups, before I was in graduate school. And you literally just, well, at that point, the hexagon doesn't go all the way around. It's just this edge. So you're just lopping off the edge of the simplex and nothing else happens. Okay, I think this is what I've got. Anybody else have questions or thoughts? Yeah, thank you for coming.
Thank you.
Thank you.
Thank you, Jeff, for a very
Good.
nice lecture. Thanks.
Yeah,
Thanks,
thank you for the invitation.